Welcome back to yet another lecture on speech signal processing. If you recall, last class I was talking about a mixture of Gaussians. So if you have a distribution or which is having multiple modes and especially if you are in higher dimensions where you cannot even visualize and you want to model this data with a in a parametric form in terms of a few parameters, right? Then we can have a mixture of Gaussian, and this mixture of Gaussian has been applied to many problems in real world. Okay, so that is a parametric kind of an approach. Excuse me. There are other cases where we might want to retain the data in some representative form rather than trying to model it with some kind of in terms of some parameters. Okay, just to give you an example. So this is the idea I had also previously talked about, that we do an idea. The idea of quantization is quite often used, right? So in fact, for heights we were saying, or even rupee, we round off to the nearest rupee. We don't go to 1.03 paisa or whatever it is, right? So what is this idea of vector quantization? So if I have something like heights and weights, correct? So this is two-dimensional. So it's a 2D vector, right? Each point representing a height and a weight measurement, right? So it so happens that there are two distinct populations. So if you can see here, right, that one of them seems I'm measured as 0 to 100, whatever it is, some variable, and therefore this population has smaller values in x-axis and also reasonably smaller values in the y-axis. On the other hand, the blue have large x-axis variations and very small y-axis variations, right? So they are clustered around this 180 to 200 mark, right? So this might be in pounds or something, correct? And this could be in kind of some inches or something, correct? So obviously 100 inches too much, but I'm just trying to say, okay? So so, or this could be centimeters or something when you're looking at children and so on, okay? So so we may want to just see what is a representative point, which is what you call as a centroid, right? That basically captures the middle or centroid, right? So like that x for that red one is somewhere here, and x for the y one is there. This is the mean of all of these. So it may not correspond to any one of these values itself, okay? But it's basically, we are trying to say that this value is sort of representative for the blue class because it's somewhere in the middle of the blue class. This sort of is representative of the red class, and therefore when a new data comes, I try to find out which one it is close to and do it. So here we are doing it basically quantizing it to only two categories, right? All these data points, it either belongs here or it belongs here, right? And every point is going to map to one of these two categories, right? This sort of thing is very useful, and in fact let me just give you an example, and you will be surprised that you use it every day. And one of the best examples is our idea of linear prediction that I keep talking about, okay? So if you recall, because I want to give you speech examples that are more relevant to this course. So for example, if you remember, we had this excitation that comes here, right? So this is excitation. The speech model, if you recall, we have done it in multiple times, right? Is either noise or something. So one of these two will be, there will be a switch that will go to one of these two guys, right? Which basically is like sounds like e, u, right? These are basically going to have the periodic opening and closing. So this is a periodic in the frequency domain. Or we have noise like fan, sat, sat, right? So this noise like thing is coming. Then we have this vocal tract, right, which basically is our mouth, and depending on the shape of the mouth, we get different resonant frequencies we talked about, and out comes the speech signal. If I'm digitizing it, including sampling and quantization, I'll get some digital signal, right, S of n, and I can analyze this, correct? So one of the things is this speech signal this part can be very well sort of approximated by something called linear prediction. Okay. So, this is basically like a filter, right? We have talked about it many times. Normally, we have something called an all pole representation for this, and the equivalent of this is that this sample, the nth sample, can be usually very well represented by some 16 previous samples. Okay, this is called linear predicting. So, I am predicting the nth sample. This is, let us say, the nth sample based on the previous 16 n minus 1 up to n minus 16 sample, and these are the coefficients of the linear combination. So, in this we try to we know also what the actual value should be, right. So, this is our model and this is the actual value, right. So, obviously, I am going to have some error, right, and so I choose my AK this Sn minus Sn hat, I can look at a square operation or something, right. I am reducing the error and choose AK to minimize, right. These are called the linear prediction coefficients. Okay, so linear prediction coefficients. And you will be surprised, today when I am talking to you over mobile phone or voice over IP or any of these methods, actual model that is used is somewhat, this was found in the 90s, I mean, it's been there from 70s. I'll come to the why that excitation, code excitation, the vector quantization part, that is where Bishnu et al. Made a remarkable discovery, and that is why today also it works so well and you do not realize. So, what happens is, obviously this part is being modeled by the AKs, the linear prediction coefficients, and so I told you short time nothing much changes, we assume over a few milliseconds they almost remain constant, right. So, this is the linear prediction part capturing the mouth characteristics, the resonant frequencies. When I say and, so a is there for a sizable amount of time during which the AKs remain constant, then then the, so and, so then these are 3 different AKs will model the 3 different sounds. And so what we do is that and these are only about 16 or some coefficients. So this is very efficient way, rather than sending this, normally remember in wideband speech I have 16,000 samples per second, and each sample can be using 16-bit per sample, right. So, it is a huge amount of data, 256 kilobits per second, and here I am talking about only 16 samples, and this is per second. And so, every 150 milliseconds or something, if I am only updating 16 parameters, it is so much reduction in the bit rate, right. And that is the whole idea, right. You want to, when you transmit also, use as few bits as possible. When you want to store also, you want to compress and store it efficiently, right. So, this idea of linear prediction started coming, but the problem was there was still this problem of what should be the excitation. So, whatever they used for excitation, it always produced some kind of a synthetic voice. Okay, so it used to sound, I am saying, some sort of, like a machine talking, very, some kind of a buzziness would be there. I can't imitate a machine talking, but you remember the olden movies, you can see that sort of synthetic voice that comes when they talk about this HAL or any of the Star Trek and all those olden movies. So, that was a kind of buzzy synthetic kind of voice that was being generated. And it's good that you can generate speech very easily, right, by using these 16 parameters, but still it's annoying, right. And today you are using, I am speaking to you, you can talk to your parents, right, on a mobile phone, your sister, your brother, your uncle, aunt, anybody, right, your teachers. you see, to you it looks very natural, as if that person's voice is reaching you. It is not. The signal is not at all reaching you. The signal at your receiver in the mobile phone itself has converted and done all these operations. Okay, so it is actually doing something smart already. Okay, and it's only these coefficients are being sent, and at the receiver, I mean, when you receive it, the signal, then you resynthesis again. Your mobile phone resynthesizes this using this equation again, and giving you the speech. Like, to you it looks very natural, but actually it has been parameterized to a large extent. Okay, one of the things that happened, which is called code excited linear prediction. So, the linear prediction part is very clear to you, which means I am predicting the nth sample based on the past 16 samples. So, if I am predicting the 20th sample, the past 16, 21st sample, again the past 16. So, as I get information, I am going to keep on predicting it, right, and I am going to update these parameters and only send the parameter across the channel or whatever it is, right. That the efficiency comes because these are only 16 or 20 or 30 or 50 parameters, and there are, it's, I'm telling you a very simple idea, but actually when there are lots of details that you have to worry about. Then comes the excitation part, and that is code excited, right. And the beauty is, Bishnu said, and this was done by Bishnu Atal. Actually, I had the good fortune of working with Bishnu in the late 90s when I was in IIT Bell Labs. So, he's an amazing guy. Okay, he's done a lot of good work in the area of speech. Okay, so so the basic idea that Bishnu realized is that if you take this is the excitation part, right, and the synthetic voice. So, even though we could capture the mouth, the vocal tract aspects very well, the synthetic part was coming because the excitation which was driving this, that was responsible for the not so naturalness of the speech. The speech was not natural because people realized that this part was not modeled well. So, what Bishnu did is he took the excitation from a large number of, I mean, by inverse filtering. I will not go into all of these ideas. So, he measured these excitation from a large number of speakers. Okay, and then he quantized this. He took some representative real, these are real excitations from the speakers, right. So, it's not synthetic like this, but real excitations that were measured, and he by undoing the effects of this I'll there are ways to get around it. So, what he did was, he took the real world excitations of large number of speakers and quantized them into 10, 24 different patterns. Okay, he said anybody's excitation will be one of these 10, 24 excitations. So, that is basically a vector quantization idea. That is, you are saying only 10, 24 points in this not two-dimensional heights and weights, in this multi-dimensional space is going to be represented by only one of these 10, 24 samples. Okay. So, the excitation is going to be only one of these 10, and this can be represented, which excitation you need only 10 bits. So, additional 10 bits will come into the parameter count, right. But basically you are feeding something which is natural, but one of the representatives. So, every speaker in the world, right. So, there are 6.4 billion people or whatever it is. He said you map it to one of these 10, 24 guys. So, which is, and then you feed it through this, and that sounds very, very, very natural. Okay. And so, this changed the way that modern speech communication works, right, voice, the way we are sending voice across channels, right. And even today we use, of course, things have improved a lot, but the basic idea still remains the same. The basic idea of all of this, both the CDMA and the GSM and all these standards basically operate on this principle. Of course, as you progress, we do some fancier and fancier things, but the idea behind it does not change dramatically. The idea is still that that code excitation is an important part. The idea is still that I can predict based on the past value something, right, the linear prediction part. These two concepts are still there, the basic building blocks on which we have made it more and more fancy, and we have done it. Okay. So, that is one of the reasons as where vector quantization plays a very important role. There are many applications where vector quantization will play a role. And so now we will talk about this idea of vector quantization. Okay, so what is the basic idea? So if you remember, I want to cluster, if I have some data, right, I want to get some representative points in that same space, right, and say these 3-4 points or these 3-4 representative vectors are good enough to represent the whole data, right. Similar to the Gaussian, but in the Gaussian I was parameterizing it in terms of means, variances, weights and all. Here I am not parameterizing, I am saying these are the 3 or 4 vectors that are representative for the entire data, right. So, there is a difference in what you are saying. This is non-parametric actually. It is actually still retaining it in the space of data points. So, let us say that I have data points like this. Okay, so there are two broad approaches in vector quantization, the k-means and the LBG, the Lindo-Buzzo-Gray algorithm, right. I think Gray is the same Robert Gray, I think. I think Professor Bhaskar Ramurthy, I don't know, he was a director of IIT Madras before. Bhaskar is probably Professor Gray's PhD student, I think. Okay, so essentially, let us say again the two variable problem, heights and weights, right, and let us say I measure some heights and weights of population, and it also happens, forget the circles, look at only the rectangle points. Okay, so they seem to be like this, and this could be because maybe there is a children, adult and male, right. So, 3 different populations can be happening. Okay, so now what we are trying to find out is how do we get some representatives for vectors for these 3 different values. So, what we do is in the k-means we assume we know the number of clusters that we want to separate out into. Okay, this is similar to knowing the number. There is a very strong analogy between whatever we did for Gaussian mixture and for the k-means or generally vector quantization. So, there we are assumed the number of mixtures. Here we are going to assume the number of clusters. Okay, and then what we do is, so let us say that I arbitrarily put some red circle, green circle and blue circle. Okay, so this is like the random initialization that I did for my mixture of Gaussians. Okay, there we initialize the parameter values. Here we are initializing the heights and weights, 3 random points I choose in this 2-dimensional space. Okay, and these are what we call as the starting initial cluster centroids. Okay, now what do I do? This is, you can see the same approach, like the expectation maximization is going to come, right. Now what did I do there? Once I initialized, and now every data point I said, does it, it was like a pattern classification problem. Does it belong to the class of males, or does it belong to the class of parents versus class of children, right. Similarly, there I was using likelihood ideas and so on. Here I am going to use some kind of distance measure. You can see in 2-dimensional plane, I can look at the distance, right. Vector distance is what? X1 squared, x1 x1 minus x2 the whole square plus y1 minus y2 squared, right. The the vectorial basically the norm, the length between the 2 points, right, the length of the vector between these 2 things, right. So, now if I initialized at the red, green and blue, every point I see is this point closer in terms of Euclidean distance. Euclidean distance is the length, right. Is this the length between this point and this point smaller than this this point and the green circle and this point and the blue circle. I assign every point to whichever is the closest centroid, right. So, it so happens that the red, so now these were not colored, they were all gray. Now, by assigning it, now I have given a label to it, right. So, now this point belongs to a red class, the green ones are closer to the green circle. So, they are labeled now with the green color, and the blue guys are closer to the blue circle, and therefore, we are giving the label now. So, similar to the Gaussian case that we talked about before, right. Now, what happens? Now, I have already got labels. So, now I know that these blue guys belong to the same category, this red guy belongs to the same category, these green guys belong to the same category. Now, what did I do? I updated the parameters in the Gaussian mixture model. Here, I am going to update my centroid, right. What does it mean? That I am going to take all the blue values and look for the mean x, by taking the mean of the vectors. So, now the centroid will move to a different place. So, this blue circle will move to a different place. The red circle obviously is going to remain here because there is only one data, and the green circle, so the red circle will move and become here, right, one data only. The green circle will move, right. So, now what has happened, the red circle moved here, the blue circle moved here, and the green circle moved here. So, the dotted was the original point of the centroid, now the centroids got updated. Now, these are the new values of the centroid. Now, again what do? I find the distance with all of the data points to which is the closest centroid it is to, and so I keep repeating this, right. That is same as the iteration that I did for the mixture of Gaussians, right. So, and if you keep doing it, finally after a certain point the clusters will not move, right. I mean they given the data points, if all the data points get assigned in the same way all the time, right, they will probably remain, or they will keep shifting back and forth between 2 points. So, then we stop and we say it has converged, right, and therefore, then all the data that got assigned to red becomes the red, the green and the blue, right, and then we have the centroid for this. Okay. So, two things, we have now a partition of the data into these 3 categories, clusters, and these are now the representative points for the 3 categories. Okay. So, one is we are separating it out into 3 clusters, and the other is of course, we also have some representative vector representing the clusters. Okay. The another way of doing the same thing is by the Lindo-Buzzo-Gray algorithm. So, it depends, depending on your experience, you might choose one or the other. So, there we assumed we knew the number of classes, and therefore, we separate it out, or we can say that first I will assume there is only one class. So, and then I take the centroid or the average of all the data points, and then I perturb. I perturb means I slightly shift and split it into 2 data points, like embryo splitting, first the first cell then becomes 2 cells, then 2 cells become 4 cells, and so on, right. So, it can grow, right. So, it is more like first the root, and then the 2 branches, and then the 2. So, this is now going to be like a tree like structure. In many computer science-ish problems, you will see this kind of a formulation of problems, right. And so, we first take the centroid, then we perturb the centroid so that we move it in either direction by a small value. So, now I have created 2 centroids. Now, these are 2 cluster centroids. So, I take all of the data and assign it to the closest cluster, and then I find that all the red are these guys and all the green are these guys. Therefore, now I have now categorized these into 2 classes after the random random finding out the centroid and then randomly perturbing it, right. And now I will get a new centroid for the green one and a new centroid for the red one. So, it will be here and here. Again, I can split the new centroid into 2 parts, right, and again the blue centroid into 2 parts, and again I find the nearest guy. So, now from 1 I split to 2 to 4, okay, and I can keep doing this, okay, and this is another way of clustering, okay. So, there are 2 broad approaches, one is called top down, or other is called bottom up clustering. So, in the top down we take one and split it into clusters, 2 to 4 clusters and 4 to 8 and so on. The way we stop is when there is not enough data to split it into clusters, one way, or the gain. So, you can also do the same thing for single Gaussian to 2 Gaussians, multiple mixture of Gaussians. If the likelihood, the way we explain the data, right, there is a parameter count, that is the number of clusters increase, I have to store more number of centroids. So, there is a cost, that is, if I have only one centroid, only one cluster, only one centroid, one vector I have to store. 2 centroids means 2 vectors I have to store. 4 means 4 vectors I have to store. So, there is a penalty that we put for, so these all come under a broad category called model order estimation, okay. So, we normally have some criteria, there are many criteria like Bayesian information, big kind of criteria, right. I will not go into the details, but there are methods that will tell you where to stop, right, and these are reasonably common sense kind of an approach, that one is if there are not much data, then stop there. No point splitting it any further. Or if they are if the clusters are not very far apart, right, in some sense, then don't further split them, because you're not gaining much. You're only increasing the parameter count or the number of representative vectors without actually getting a benefit. So how we use that stopping criteria is something that you can worry about. The point I want to say is this is also one approach, unlike the Gaussian mixture model, right? But this is also useful. But depending on the application, you might use one or the other. Okay.